Okay, so I think we should start this session. I happen to be the chairman of the session on the first speaker. I guess that's the trick of the organizer to make sure that the chairman. So I will try to keep the time as my own chairman, and then we will go to the other presentation, which I will share. Okay, let's start. So this contribution is about the effect of specimen size and thickness and shape, actually, on the measure of toughness. It's a purely numerical work, and that's a work I'm doing together with Thomas Pardoen at UC Louvain. Probably know, if you're familiar with ductile fracture, you probably know Thomas Pardoen is very well known in the field. So if you look at the literature, and in particular, here these are pictures taken from the very well-known handbook from Anderson. There is this trend that there is an evolution of the measured toughness as a function of the specimen thickness. So on the left, you cannot see it, but in the legend it's written that this is an unspecified alloy. So I cannot tell you what it is, but that's in the book. So you see that apparently if the thickness is very high, you have some kind of plateau. When you reduce the thickness, it increases and then tends to decrease. So bump like that. On the right-hand side, that's an aluminum material, and it seems that it's continuously increases as the thickness is decreased. So the aim of this study is fairly simple. We want to try to simulate this thickness effect and understand the origin based on FE simulation. So we're using a non-local GTN model. So I will be quick because I already presented it in the plenary session, and I will focus on the simulations. So here you have the equations for the local standard GTN model. Once again, you have void growth and damage nucleation. As I already presented, the model is known to show very strong localization due to mesh dependence. It's not only mesh size, but also mesh orientation and so on. So we wanted to get rid of that problem and used a local model. An important feature of the model is also that you need to resolve the coalescence. So here's the equation that is in the original GTL model, where you introduce a critical porosity, FC. And when you reach this porosity, you enter the coalescence regime. And there's a nice alternative, which was proposed by Zilian Zhang a long time ago, 1999, which is based on the Thomasson approach of coalescence by internal necking. And basically, when you reach the coalescence criterion given by Thomasson, the porosity level you have at this point is considered to be the critical porosity. So you don't need to fit it anymore, and that's very, very useful. And then I'm also using the formula proposed by Zilian for the porosity at the rupture. And in practice, this avoids fitting FC. In all the calculation, I get an FC which is between, let's say, 1 and 5%, which is completely consistent with unit cell calculation, for instance. Okay, so we use a very simple nucleation model. So as previously, I said, okay, we have coarse particles. So we consider the volume fraction of coarse particle as our initial void volume fraction. And then we have a very simple nucleation law, which is given here. So the rate of nucleation is 0 below a critical strain. And when you go above a critical strain, it's a constant. Once again, it's a purely numerical study, so we can basically do what we want. Indeed, we could use more sophisticated models, but this would need to be fitted on experiments. Okay, and I can show you some example that this is not just a dream, that we have two nucleation mechanism. That's actually true. So on the top, it's an X100 pipeline steel. So you have the smooth tensile bar as ST, low triaxiality, very fine dipples initiated on carbides. On the left, sharp, very sharp notch bar. high triaxiality, and you get much larger dimples, no secondary duplication. We have that also, we observed that also a long time ago on aluminum in a cracked specimen. High triaxiality, we get large dimples, that's the picture on the left, and low triaxiality, secondary indication. So that's really a mechanism that is existing. Okay. So here we use a non-local model, as I said. It's a different strategy as the one I presented before. It's based on an implicit gradient technique. And here we use actually two length scales, one for growth and one for nucleation, because you see from the picture that the length scale are not the same. The one for nucleation should be smaller as the one for growth. How small, that's a problem of computation, but it should be smaller. So we use two non-local length scales to represent the two different damage processes. So in this study, we used 100 microns for growth and 1/3 of that for nucleation, which is obviously too large, but it's very difficult to go to much smaller mesh sizes. Okay, so we carrying a lot of simulation of only CT specimens. We use side grooves, and we have two types of specimen. You have homothetic CT specimen. These are like Russian dolls. That's the same specimen, but it's either it's expanded in the three directions. So Russian doll specimen, I would say. And there is one which has the same profile and different thicknesses. So that's the second series. So we have a width of 25 millimeters. So if you follow the standard, what they advise is to have a thickness of 12.5 millimeter. And so you went down to 1 millimeter, very thin sheet. And we went up, these are very weird specimens, which are very thick, up to 25 millimeters. This one, I never saw such specimen being actually tested, but that's something you can do. The same for the homothetic specimen, Russian doll. We went down to very small thickness, 3 point something. These are specimens, it's easy to run, it's very difficult to machine and test. So we use and we are going to use different set of parameters. The number of degrees of freedom goes from 22,000, which is very, very small, to almost 2 million degrees of freedom, which takes much more time to compute. Okay, so here are example of the homothetic Russian doll specimens. What is important is that it's not the same mesh which is expanded or shrink. It's a specific mesh because where the crack propagates, you need to have a very small mesh size everywhere. Okay, and I'm propagating the crack up to 2.5 millimeter, and these are the constant shape, different thicknesses specimen. Okay, so you can see always a region where the mesh is very, very fine, and with that we can generate J delta A curves as much as we want. The way we determine the J delta A curves is we consider the simulation as tests and actually running using the same routine for processing experimental data and processing these simulations. Okay, so here's an example for a homothetic specimen. You don't see much scatter. It's very, very close to each other. And here, that's the same kind of curves with varying thicknesses specimen. There's much more differences. And what I'm going to use is the J05, so J for a crack advance of 0.5 millimeters, which is defined by the third exclusion line here. Okay, so and here are the results. So here I have JO2 and JO5, but I'm going to focus on JO5, and you see that the difference is not very, very important. So that's a case where we have standard Q1 and Q2 parameters for Gerson, almost no nucleation. So you see that for the homothetic specimen, we more or less get a constant value for J, whereas for the varying thickness specimen, J is continuously increasing as we decrease the thickness. Okay? Let's move to another one. And how can we explain that? We look at the stress triaxiality ahead of the initial crack tip at about 1 millimeter ahead of the initial crack tip. And you have on the left the evolution of triaxiality for the homothetic specimen. So you see that at the beginning, for a lot of geometries, the triaxiality is not changing so much. So the triaxiality here is plotted as the plastic strain at 1 millimeter ahead of the initial crack tip. And you see that the failure strains are more or less in the same range, around 30%. If you look at the specimen of different thicknesses, then you see much more changes in stress triaxiality ahead of the crack, which leads to a strong variation in the local strain at failure. And that's the reason why we get that kind of behavior, almost constant for the homothetic specimen and strongly varying for specimen with different thicknesses. So now you can play with the model. So here, for instance, I can generate specimen with with different initial void volume fraction. So for the homothetic specimen, I get always the same trend, almost constant. Indeed, if I reduce the initial void volume fraction, the toughness goes up. If you vary the specimen, you get always that increasing curve, unless you have an initial void volume fraction which is very low, so that you can strain the material a lot, and you can reach a point where you start to have secondary nucleation. In all the other cases, you fail by internal necking without reaching the strain which is needed to trigger nucleation. And that's why the curve is always increasing. Okay? So we can play with the different nucleation rates. Basically, what you have to conclude from that is if you want to have the bump, it is you only get it if you have nucleation. Without nucleation, you cannot get the max of the fact that the toughness increases and then decreases. You can obtain that only by adding nucleation together with growth. Because here what I did, that's a model, you can easily play with it. I say, okay, no growth. On the GTN model, this corresponds to setting Q2 to 0. Okay? It's not very realistic, but it helps understanding what's going on. And you see that for the homothetic specimen, it goes down, more pronounced. The reason for that is that basically, in that case, damage is not influenced by triaxiality, but triaxiality is still there. So if you have a high triaxiality, you develop higher stresses, and the energy you dissipate is higher, so you get a higher J value. And you get the same effect for the varying thickness specimen, that the effect is nonlinear because of purely geometrical effect of the specimen. Okay. What is also interesting is to have a look at crack path. So you see here example of crack path with different values of the initial void volume fraction, the effect of nucleation. If you have only growth, you tend to have very curved crack fronts, which are not always observed. Which means also that looking at the shape of the crack front could help you fitting your material parameter. You should have a material parameter that fits the overall behavior, but also the crack front. Okay, here's another example for specimen with different thicknesses. When the specimen is very thick, you tend to have a straight crack front in the middle because there's no strain or strain gradient along the thickness direction. Okay, and then we can come to some conclusion. So the main conclusion is that when we use homothetic Russian doll specimen, there's not much effect of the thickness on the J values. That's not the case when you're changing the width of the specimen by keeping the same profile. And the trends we see in the literature may be because that people have used a mixture of those specimens, and you have to be very careful. The conclusion is also that toughness does not only depend on the thickness of the specimen, but also of its overall shape, which makes interpretation of test even more complex. The problem is also how to get the correct path. Okay, so